This is Dr. Hamid Isazadeh, and in this lecture we will be talking about metal forming. In the book, in the textbook we have 3 chapters. Chapter 17, fundamental of metal forming, this one, and chapter 16, bulk deformation process in metal forming, and sheet metal forming. So in this lecture, we try to cover these 3 chapters. What is metal forming? Metal forming is a manufacturing processes in which plastic deformation is used to change the shape of metal workpieces. And we have plastic deformation in metalworking, and it's very important. And the plastic deformation is a permanent distortion that happens when a material is subjected to stresses. Stresses can be tensile, can be compressive, can be bending or torsion. So these stress has to be above the yield strength to cause the deformation. And what is the yield strength? The yield strength is a stress that material can withstand without permanent deformation. Let me give you this example. Here we have a stress, a strain plot. This is a stress, this is a strain. Okay, and then we have a dog bone sample. Then we pull apart the 2 ends of this dog bone sample. What happens because of that, pulling, we have stresses at the part. As we pull apart, we have some elongation, then we have some stresses. And we normally for metal, we get this type of strain stress curvature. As you see, up to a certain point, we have a linear plot. Linear means, it's a straight line. And up to some point. After that point, we have some, a nonlinear curvature. So up to this point, in the linear plot, if you remove the stress, if you remove the load, the material, that workpiece comes back to its original position, because we have up to here we have elastic deformation. It's called elastic. But after that, that threshold, which is this threshold is called yield strength. We go to plastic deformation. It means the material doesn't come back to its original position, original shape. And we use this, behavior in the metal forming. If we didn't have that, behavior, we couldn't do any rolling, any forging process or extrusion. That behavior is very important in metal forming processes. Some metal forming uses compressive stress, like rolling, forging, and extrusion. As some other forming processes uses tensile stress, like cutting or drawing. These are some of the processes that we use tensile stress to deform material. There are some material properties that make a metal or a workpiece a good candidate for the metal forming. Some of these desirable properties are low yield strength and high ductility. If you have material with a low yield strength, means that you need a lower amount of load to deform that workpiece. And high ductility means the metal or that material can be stretched without any failure. And these properties are affected by temperature. Ductility increases if temperature goes up. Yield strength decreases as the temperature goes up. So as you see, if the temperature goes up, these properties become more favorable. There are other factors that we discuss later: a strain rate and a friction. These affect the metal forming processes as well. In the metal forming processes, we have two categories. One is bulk deformation, and one is sheet metal metalworking. Under bulk deformation, we have four processes: rolling, forging processes, extrusion, and wire and bar drawing. Under sheet metal working, we have bending operation, we have deep drawing, we have shear processes, and other processes. But what is bulk deformation? Bulk deformation generally means that we have significant deformation and massive shape changes, and the surface area to volume of work is relatively small. Let's look at this example here. So we want to see surface over volume. Okay, so in the bulk deformation, surface over volume is small, and if you calculate the area of this shape, you can find out the surface over volume for this one is smaller than this metal. So surface on this sheet is larger. In general, in the sheet metal forming, we are dealing with material with a thin thickness. In this slide, we have couple bulk deformation processes. The starting workpiece can have very simple geometry, like a cylindrical billet or rectangle bars. The first figure, the first schematic, shows a rolling process, and we have a severe compressive deformation, and the thickness of that plate or a slab is reduced because of these two rows. These two rows are drawing this workpiece into this gap, and the gap has a certain distance, and the thickness of this workpiece is reduced as the workpiece goes inside the gap. Then we have forging process in this picture. In the forging, we have a workpiece that is compressed between two dies, two opposing dies. This is one die, and this is another die, and the force is applied, from up toward down. And the die shapes, are imported to the workpiece. The forging, traditionally, it's a hot working process, but there are some forging processes that are performed in cold environment. The third process is extrusion here, where we have a compression process. The work metal is forced to flow through a die opening like this one. As you see, we have a die, and the part will take the shape of that opening. It becomes, smaller. The cross section of this material, this workpiece, becomes similar to shape of that die. The last process is this one, and it's called drawing. It is another, forming processes where the diameter of a round wire or a bar is reduced by pulling it through a die opening, right? So these two processes, this one, C and D, are very similar, but as you see, the force that are applied to the workpiece is different. So the force here applied at the right part, it's somehow is pulling the part, but on the left one, the force is going to be applied to push the part. So that is the main difference between these two processes. The next category is sheet metal working, and sheet metal working is mostly the operation are performed on the metal sheet, strips, and coils. And these processes often are called press working because the operation are performed on presses. And we have three subcategory in this process. One is called bending, another one is called deep drawing, and then we have shearing. In the bending, actually, the bending involves a straining of a metal sheet or plate to take an angle along the straight line. So we apply a certain load until we get desired angle on this workpiece. It's called bending. The next one is drawing. As you see here, deep drawing, it refers to a forming of a flat metal sheet into a concave shape. It can be a cup. So originally, this workpiece was flat. When we apply this punch, toward down this way, that cup will take the shape of this punch. The next operation is shearing, where we use the punch and die to create some cut on the workpiece. In metal forming processes, there is a term called flow stress, and this flow stress is important because it impacts some factors in the metal forming processes. The important one is the load. The load in the rolling process. How do you want to determine the load? So you need to calculate the flow stress, how much stress is going to be applied to the part. So if you calculate that value, then you can calculate the load required for the process. And the flow stress um, is changing. It is instantaneous value of a stress required to continue the formation of the material, and that can be calculated from this by this equation. This part is flow stress, and this is the strength coefficient, and this is strain hardening exponent, and this is the strain. And here we have a plot of a stress versus a strain, and it shows here we have a linear curvature, elastic curvature, and after that we have a nonlinear, which is the plastic deformation. As you see in this plot, the stress keeps increasing as you apply strain. Why the stress goes up after yield strength, after the first deformation? The main cause is called a strain hardening, and that is a process of making a metal harder and stronger through plastic deformation. When a metal is plastically deformed, we have dislocations in the metal that are going to move, and these dislocations are generated and become more and more. Dislocations, as we talked about dislocation before in the material in alloys, when you apply load, you have plastic deformation. This defect, dislocation is a defect. Dislocation will tangle to each other, and it makes the deformation, plastic deformation, harder and stronger. In metal forming processes, temperature has a major role on these parameters, the K parameters, N parameter that we discussed in the previous slide. As temperature goes up, the strain hardening coefficient or exponent here and strengths, the initial strengths, are reduced. Also, ductility is increased at higher temperature. Ductility is favorable. We want ductility be higher, be more in the metal forming processes. Here we have two pictures, this one and this one. These are tensile test samples. One is aluminum alloy, the other one, the right one, is cast iron. Aluminum alloy is more ductile, so as you see the necking, this part, so the part was stretched more before no failure, and this one didn't go through any ductility, so elongation was less before rupture. But in general, ductility is a measure of material's ability to undergo plastic deformation before rupture. And normally, deformation processes, deformation operation can be performed with lower force and lower power at higher temperature. Based on the temperature, we have three processes: cold working, here, this one, we have warm working, and we have hot working. cold working process can be performed at the room temperature or slightly above the room temperature, and many of the cold forming processes are important for mass production operations. When we do cold working, we normally we have no machining processes, or maybe very uh, some small amount of machining is required. They are called near net shape. So once the process is done, it's ready for use. What is the advantages of a forming process? It has high accuracy. It gives you a closer tolerance. You have a better surface finish, so that's why you don't need extra machining process. Because we are performing the process at low temperature, strain hardening is going to be um, higher at the room temperature. Because of that, the strength and hardness of the part are higher in the cold forming process. In the cold forming, the structure of grain um, will be changed. For example, if you have grains, you remember we have grain in the metal alloys, or metal, or pure metal, or any alloys, and these grains has a one original shape. When we deform it through cold working, they will be stretched in one direction, like this. If you apply rolling process, apply force up and down, these grains are squeezed down. What happens, um, the grains becomes smaller in one direction, so you have some anisotropic property. So that's why it's called directional property. If directional property, if you want to have a harder strength in the in this direction, because uh, these grains are boundary are closer to each other, and the strength in that direction is going to be higher compared to this direction. So it might be favorable in some operation. Another good thing about this process that we don't need any apparatus or equipment for heating, because we are performing the process at the room temperature. But there are some limitations, some problems with this cold working that we have to consider. First is that because we are performing the process at the room temperature, we need more forces. We need higher force and power for the formation. And the starting workpiece um, should be clean. It shouldn't have any no oil, dust, or dirt on the part. And ductility is one thing that we have to consider in the cold working, because ductility, some of the material are not ductile, so we cannot apply too much stress in the process. The next metal forming process, um, considering the temperature, is called warm working process, which is performed at room as temperature above room temperature, but it is below the recrystallization temperature, where the new grain can um, be formed, And this temperature is a function of melting point. If you have a material like a steel has a 1500 degree Celsius, you can perform this the process at this temperature, 0.3 times that melting point. This is the equation. So it will be 450 degrees Celsius. So this process has to be done around this, this temperature. And the advantage is that because the material is hot, we need no lower force. It can be deformed easily. So we need lower power or lower forces. We can have a workpiece with a complex geometry, and the need for annealing can be reduced. Annealing is a process that can reduce stress. When you make a part and in the manufacturing processes and you left some stress inside the part, it's called residual stress. Residual stress can be removed by annealing. But if you perform work, warm working, then the need for annealing can be reduced. The disadvantage of this process is that the workpiece must be heated. So you need, apparatus to heat up the part. So that is the limitation. The next process is a hot working process, and this one can be done at a temperature above recrystallization temperature. And the temperature approximately you can calculate it by this equation, 0.5 times melting point. Again, if you have a steel has a melting point of 1500, multiply 0.5 by that 1500, that it gives you 750. This is about the temperature you need to work. And why do we need hot working? Because if we want to do, for some material, for some cases, if we want to do the process at the room temperature, cold working or warm working, we need, more stress, more load, because of the plastic deformation. At that temperature might be too much, and it cannot be handled. So they increase the temperature, so the load for plastic deformation can be reduced, because that value K, as I mentioned before, the strength coefficient is substantially less than the value for the room temperature. And at the high temperature, that n number, the exponent, becomes zero, theoretically. And ductility also increases at a hot temperature. Here are the advantages of a hot working process. The shape of work part can be significantly changed. We would need lower force or lower power, and those metals that fracture at cold working, they can be processed at hot forming process. And the strength of the part, the workpiece, become isotropic in the hot working process. It means the material property is going to be isotropic. It's going to be the same in all direction, x, y, z. and the part will have no strengthening. So because it doesn't have any residual stress left in the part by the hot working process, um, then it's called no strengthening. So you don't need any annealing process to remove the residual stress. There are some disadvantages for the hot working processes. Is lower dimensional accuracy. The accuracy goes down with this process. You need more energy, the total energy, because you need to heat up the part. Thermal energy is needed. And the oxidation may happen if the part is exposed to some gases in the atmosphere, which is not favorable, for example, nitrogen. Then you will have a poor surface finish. And the tool life in the hot working is shorter. Besides the mechanical property, there is another phenomena that affects the metal forming processes, and it's called strain rate. And this strain rate in metal forming is related to the speed of the formation. If you look at this, the strain rate is defined as the velocity of the ram or the movement of equipment over the height of a workpiece or instantaneous height of workpiece. Here we have a plot of flow stress over the strain rate. As you see, for this plot at room temperature, if you increase the strain rate, it means the ram or the punch moves faster at a room temperature. The flow stress changes um, slightly. It doesn't change much. But as we go higher temperature, for example 400 degrees Celsius, we were working at that temperature. So temperature is high, but if you change the strain rate, if you work, for example, here this one at a one strain rate, you see you have this flow stress. So you need that much stress to create the formation. But if you increase the strain rate, you go, for example, to 100. This is 100. So the flow stress goes up. So it is important to calculate the strain rate to find the um, respective flow stress for that application. In metalworking, um, we use a lubricant because it can be applied to the tool and work interface in the forming operation to reduce the harmful effect of friction. And in most metal forming processes, the friction is undesirable because of these three reasons. Metal flow is reduced, force and power will go up if you have friction. You will have wearing in the tool, so the life of the tool reduced. So here are the benefit of using lubrication in the metal working processes. It reduces the sticking, and it reduces the amount of force needed for the formation, or it gives you a better surface finish. It gives you um, less heat which is important. So if you have less heat, the tool, the life of tool is gonna go up. For the processes, we start with the bulk deformation, and the bulk deformation, as we mentioned before, the surface over volume is small. So that ratio, surface over volume. So the material that we are working has a smaller ratio of surface to volume. So the starting form are cylindrical bar or billet. They can be rectangle, they can be a slab. We don't work with the sheet metal in this process, and we need large amount of force to cause a plastic flow or plastic deformation until we get the desired shape. And this process can be done at the room temperature, at cold or warm or hot or high temperature. And we have a rolling process. We have forging under bulk deformation. We have the extrusion, and the last one is wire and bar drawing process. The first process is the rolling process, where the thickness of the material is going to be reduced because we have a slab or plate going between the two rolls, as you see in this picture. These are rotating in the opposite direction, and then the material will go into that gap between these two rolls, and the material is going to be squeezed. This process is also called flat rolling. It is used to reduce the thickness of a rectangle cross section. The rolling processes, we have various types depending on the workpiece geometry. It can be flat rolling, it can be shape rolling, and based on the work temperature, we have two types. We have hot rolling and we have a cold rolling process. Here are some examples, rolled products made of steel. This bloom was um, turned into a structural shape, beam, like a beam, or it can be shaped like a rail track. A slab was turned to plate or sheet or a coil, this one. Also, the billet was um, shaped into bars or rods. There are some terms related to flat rolling process. As you see in this picture, we have two roller. Um, this one is rotating this way, and this one is rotating clockwise. And there is a term called draft. The draft is the amount of thickness reduction that can be calculated by initial thickness and the final thickness. If you deduct this value from each other, then you get the draft value. And the reduction is another term. It's a draft expressed as a fraction of a starting stock thickness, and this is a reduction. We talked about flat rolling. Now we have shape rolling, where the work is going to be deformed into a contoured cross section rather than flat shape. And this can be performed by passing the workpiece through rolls that have no reverse of the desired shape. And here are some products of the shape rolling. They can be I-beam, they can be L-beam or U-channel rails for the railroad tracks, or around the square bars or rods. These are products of shape rolling process. Most rolling processes are very capital intensive and they require massive pieces of equipment, and it's called rolling mills. The, and they have various type. One is too high, where we have two rolls, or three highs, which is this one. We have three rolls. The workpiece goes this way first, and then it comes um, as a raw material for this part. Or we have four highs, or here we have a cluster mill, or this is a tandem rolling process. So continuously the thickness of the part is reduced. This picture shows the rolling mills. As you see here, the glowing strip in the lower left corner, it's a steel plate and it's going this way. There are several rolls there, so it can reduce the thickness of the part in one step. And the heating operation here is called soaking, and the furnaces um, where we use here is called soaking pit. And the raw material can be bloom, can be slab, and billet. We have other deformation processes which are related to rolling process. It's called thread rolling. We have ring rolling. We have gear rolling and roll piercing process. Here the first process is thread rolling. In this picture, the process is shown for you. Um, the process is used to form threads on the cylindrical parts by rolling them between two dies. As you see, we have two dies that are moving. One is fixed, this one, and this one is moving. So it forms thread on the cylindrical shape. This process is important for mass production of bolts and screws. They can be performed at in the room temperature cold working process. The advantages is that higher production rate, and the threads in this way can be stronger and they are better for the fatigue resistance. Here we have ring rolling process as shown in this picture, and this is the one type of deformation process where a thick wall ring of smaller diameter is going to be rolled into thin walled ring with a larger diameter. As you see, this one is larger than this small ring, and normally this process requires high temperature, so this can be done at a hot working environment. Products are ball and roller bearing races. Also, it can be used for pressure vessel and rotating machinery.